Hello, Physics Land! So, what we're going to do is we're going to look a little bit more at what you figured out as you were doing Walk the Graph Lab. So, I hope when you were able to do it, you were able to get a line that was hopefully even closer than this one when you were walking in. Yay! When you're doing this, then, I want to talk a little bit about where was your origin? What was positive? What was negative? And then use that to start to look at this idea of what the physical significance of the slope for the velocity versus or for position versus time, and then also the area for velocity versus time, and what that all physically represents. So, let me pull up on my computer, my iPad. All right, so what we were going over here, we saw that originally we were at rest, right? Phase one is at rest. So if we're looking at a VT graph, phase one would be zero, velocity of zero. After that, during phase two, we see over here that we were actually moving, and we were moving, and in this case, the slope is showing that it's moving in the positive direction at a constant velocity. Which brings up a really interesting question. When we were working with our motion detectors, so this is my little motion detector, okay, and you're standing over here in front of a motion detector. Remember, first of all, where's our origin? And if you kind of think about it, our origin is actually going to be our 0 meter mark, and that's going to be located at our sensor. All the position values were measured relative to our sensor. The other piece, too, is that as you walked backwards, it actually was considered the positive direction. So, positive direction for a motion detector was away. In other words, when the position values were getting bigger, you were moving away from your sensor. So as a result, during phase B, when you were moving away, you really had a positive velocity. So we had a positive constant velocity. And remember when we talk about constant velocity, we're talking in this case about a flat velocity on a VT graph. Velocity staying the same. Then after that, during phase C, it went back to staying at a constant position value. In other words, you were at rest. During phase D, you can see that you have a negative slope, and a negative slope would tell us that we have a negative velocity. And then during phase E, we have a flat line for our velocity. In other words, it's staying at rest. Oh yeah, hey, if you hear the whistling, that's my bird, Jack. Hey. Okay, so anyway, we're looking at this graph that looks like this. So what we want to do as we go along is figure out how are these things connected? How is this line, this sloped line on my position versus time graph related to the velocity versus time graph, this rectangle that we have here on our graph? So to be able to do that, I want to focus in on just phase B. So if you look at phase B, you'll see that during phase B, we actually went from 1 second till 3 seconds. So in other words, we had a total change in time of 2 seconds. And during that time, we went from 1 meter to about 2.5 meters. In other words, we moved back, we displaced ourselves 3.5 meters. So if I want to find my velocity, remember I'm on a position versus time graph. So if I want to find my velocity, I want to find my slope. So remember my slope on a position versus time graph is equal to my v, my velocity. So if I want to look at my slope during phase B, I'm looking at a rise of 0.15 meters over a run of 2 seconds. So pull out your calculator and plug it in. So, and when you plug it in, pause if you need to. Yep, I really mean it. Pause it. Yep, okay, plug in your calculator. What is 1.5 divided by 2? Yes, exactly. It is 0.75 meters per second. In other words, you are moving backwards by 3/4 of a meter for every 1 second. So 0.75 meters. So when you look at your area graph, and this is kind of zoomed in a little bit, this is what your area graph should actually look like. You actually had your phase B as being at a level of 0.75 meters per second for your velocity. So now the question is, what is the physical significance of this graph, of this area? So this is a VT graph, velocity versus time. And we want to figure out what's the area of this box, or area under the curve, which we'll talk more about later on. So the width of it, okay, so the width went from 1 second till 3 seconds. Okay, so 1 second till 3 seconds. So in other words, the width of my box is 2 seconds. And the height is 7.5. I'm sorry, 0.75. My bad. Let's change that again. It should be 0.75. So in other words, my height is 0.75 meters per second. So it's an area of a rectangle. So if I want to find the area of this little guy, think back, how do you find area of rectangle? Basic kind of geometry there. Length times width. So my length is 2 seconds times my width of 0.75 seconds, or 0.75 meters per second. So my area is 2 times 0.75, or 1.5. Okay, my seconds cancel. So 1.5 meters. Huh. 1.5 meters. Meters. When we think about meters, when we talk about meters, we know we have units of meters that go and work towards things like distance, things like position, things like displacement. So when we see that there are units like that, we know everything is physical significance. So we know that this box, this area under this curve must mean something. So let's think about this. Where have we seen this number, the 1.5 meters? Here it is. 1.5 meters was our displacement. Coincidence? I think not. So in other words, when we look at this area is actually our delta x. So the area under a velocity versus time graph is equal to the displacement of my object. It's equal to the displacement of my object. And in this case, it was 1.5 meters. In other words, you move back 1.5 meters during those 2 seconds. So when it comes to this, what you'll notice is that your graph probably didn't look exactly like this VT graph. Your VT graph, even though the box was supposed to look like this, your VT graph probably looks something like that. Okay? Something along those lines. When we talk about the area under the curve, it applies even for irregular shapes. So I could find the area of this shape by finding the area of this irregular figure. So what I want you to do is go back to your graph, go back to your velocity versus time graph, and the integral or area that you got, and see if it's pretty close to the 1.5 meters. Even though you didn't look like a perfect little rectangle like we'd expect, you still should get somewhere pretty close to the 1.5 meters. So when we talk about area of this curve, it really just means the area between the axis and our line or our shape, our function. And the area between that is what we're going to call as our displacement. So when I look at something, let's say like this is a VT graph. Let's say I want to figure out what was my displacement between 0 and 3 seconds. What was my displacement? And because I'm looking at a velocity versus time graph, I know my displacement is going to be bound by the 0 to the 3, the axis, and then the line. In other words, the area of this particular shape represents the fact that during this graph, I had a displacement equal to the area of the triangle. So in other words, my area of my triangle, in this case, was 1/2 times my base of 3 seconds times my height of what looks like 12 meters per second. And if we go through and we do the calculations, we'll see that the area, which is equal to your displacement, is actually equal to our 18 meters. So 1/2 times 12 is 6. 6 times 3 is 18. So anytime we find that area of that VT graph, that's your displacement. So apply all this fun stuff. I think your next step is looking at problems number 4 and 5 on the constant velocity problems. Keep moving along. Let me know if you have questions. But once again, we're seeing that everything in physics has physical significance. The area is what we call in calculus the integral. The slope, that's what we call in calculus the derivative. All these things all connect. They all have physical significance, and they all tell us something about the object's motion. Have fun, physics land!